a lot of stuff to do today. So, but first, before we get started, I want to give a very quick review of what we've seen. So this you don't need right now. So past weeks. Okay, so this is just a reminder of what we've seen. We've seen, all right, we've tried to answer the question, what is a diffraction problem? So that was just essentially boundary value problem to this differential equation. Then we have seen in the last 2 weeks how can we view complex analysis. In one variable to solve problem. And we've also seen how we can use complex analysis to obtain, well, let's call it in-depth understanding of physics. So what I mean by that is that last week we have seen that using Cauchy theorem a bunch of times, we found that the scattered field splits as a diffracted field, and we have also recovered the classical geometrical object component. So we've got a more like physics understanding just by using complex analysis, and then doing some approximation, we found this nice, this really nice path approximation, right, where we had this limited wave plus the reflected wave. So this is sort of everything that complex analysis could do for the problem that we consider. So, and how this worked was essentially use Fourier transform, and then we have some formula like this, right? Which you can add. So this is the whole idea as to how complex analysis comes about, right? We treat this phi as a function of a complex variable alpha, and then we can use complex analysis methods to analyze this contour integral. That was the whole idea behind what we did last week. Okay, so now this does not work all the time. So this does not necessarily work. It works a lot of times, but there are problems for which for which maybe it works, but we have not yet figured out how it works. So, what are two problems for which it doesn't work? I will not write down the whole formulation, so this is just to roughly give you an idea of what type of problems we do not consider using everything we've seen in the past 3 weeks. So, one, if we are in 2D, so that means that we are in R2, we could consider, for example, a problem like this. You have a wedge here, and you have a wave number K2 inside, K1 outside. You consider a plane wave, for example, coming in like this. And let's call this omega. And then here we have R squared without omega. And then we would have some system of equations like that, right? We would have that U satisfy this Helmholtz equation with one wave number in R squared without omega, and it satisfies another Helmholtz equation, so with another wave number in omega, and then you would need like 2 interface conditions. So that is just to say, we need to, hello Redana, this is just a review. So for this type of problem, we would need 2 boundary conditions across here, right? We have Dirichlet or Neumann. So if we assume that nothing happens in here, then one boundary condition is enough. But essentially, because we have 2 different fields, we need 2 different boundary conditions. But what exactly these interface conditions are doesn't matter. But you can look it up in my thesis, for example, if you're interested. Exact formulation of this type of problem, plus 2 interface conditions, and then radiation condition, and energy condition, and so on and so forth. So this is the first type of problem that we couldn't apply all of this. Like, so you can apply one complex dimensional analysis to it, but this final point as to getting this in-depth physical understanding, I think is what we can't do with this. So we can use one complex variable to get a lot of numerical computations for this problem, but we can't solve it analytically. The same goes more or less for the second problem, which is now completely in 3D. So this is still a 2-dimensional problem. Right now we just have the transparent scatter out, so non-perfect boundary conditions. But if you want to look at a problem with perfect boundary conditions that you don't know how to solve, if I don't know how to solve, I mean analytically, we could have this quarter of the plane right here. So this is just sort of this over here, right? It's in 3D. I have 1/4 of the plane, so this is R3. Let's call this over here omega, and then we would have a wave number in here. Again, plane right incident over here. Plus Ira Dirichlet and 1 omega, and again radiation condition, energy conditions, and so on and so forth.
So Valentin, sorry, I was a bit late. So these 2 examples are instances where the approach you have described in one complex with one complex variable so far does not work.
Yes.
Okay.
Which you have to take with a grain of salt, because a lot has been done to try to make one complex variable methods applicable to these problems, and you do get a lot of results, but they are mainly of numerical.
They're mainly
numerical. So what this means is, using one complex variable last week and the week before, we have found what we would call a closed form solution to the half-plane problem. As we had an exact formula, everything inside the formula, we knew exactly what it is. We had some line integral, and underneath that we had some rational or algebraic functions and some E functions. But this is all things that we understand perfectly well, and the computer knows exactly how to handle. We could use a method of steepness descent or just contour deformation to recover the refracted field and the reflected field. And this closed form solution we do not yet have for these problems. And this is what I mean by saying this does not work. It is not necessarily true that you can't force one complex variable analysis onto these problems. You can do it, but and you can get useful information out of it, but you can't completely solve it. So we would say that these problems are like partially solved, but they're not completely solved. So but I can't really do all of the work that has been done on these problems just because almost 100 years, well, yeah, almost 100 years of mathematics, and but there is for wedge, not necessarily for if you are really interested in the history of the wedge, I think Matthew Nethercote's thesis, which I think I sent you the link in the WhatsApp group, has some, well, it has an excellent review article on perfect wedge diffraction, where you would just have Dirichlet, Neumann, or Robin boundary conditions on here. which we know completely how to solve. And it also has a really good overview of work that has been done on the transparent problem. So that's probably a really good reference if you want to look at this. If you want to look at this, the best reference I know on the history is Rafael Assia's PhD thesis, but I don't know if that's publicly available. But I can try to dig up some references if you're interested in the history of this problem.
Did you take a look at Matsainat? Because now Matsainat publishes everybody's thesis.
No.
Whether it's published or not, they're posted on Matsainat, so it might be there.
I have not checked.
Take a look.
So, and I could maybe, let's call this, sorry, I completely forgot the U. So this should be U twigger equals 0. So, however, what we can do for F equals U, so that would be for problem number 1, or F equals U twigger, we can write something like this. And do not worry so much about all of the details, because this is the motivation for the rest of today's lecture. So we can write something like this, where as the last weeks, this is either the imaginary part of K or the imaginary part of K1 and K2, right? So this would be for problem 1, this would be for problem 2. The important point is that this is some positive parameter. We can write it like this. We can write it as a double Fourier integral. Oh, sorry. Yeah.
And we get where f is where what problem are we looking now?
We are looking at either of the two problems.
Okay. And f is the source.
No, f would satisfy either of these problems.
Okay.
But
You suppose that you know the solution, right? You know the solution?
No, well, I know that both of the problems are solvable. So I can pretend that I know a solution even if I don't have a formula.
Okay.
Okay, sorry, yeah. So I know that U and U twigger exist. Well, we just don't know what they are exactly.
So you're looking for a representation formula assuming the existence of this.
Yes, exactly. And well, not exact representation formula, but what we can do is we can write it like this. Where this is a suitable spectrum function, which I will not tell you more about for now, because this is a function in two complex variables. So this is our motivation to start to study several complex variables now. But this, I would just say, is a suitable vector function. And do not worry about the details of all of this. Like this is just my motivation for what we do today. And if we have time at the end of this lecture, like not necessarily today, but I mean in 2 weeks, then I will give you more details on all of this for either of those problems. But for now, the motivation is that, you know, we cannot necessarily write it nicely as a Fourier integral. We cannot necessarily represent our field as a Fourier integral in one complex variable, which we did for the half-time problem. But we can write it as a Fourier integral like this.
So it's the integration is over R2,
Yes.
both for problem 1 and problem 2.
Yes, that is correct. But for problem 1, what you would do is you would, so the idea for problem 2 is that you would use the double Fourier transform, kill off, then you get an ODE, because this is a 3-dimensional problem. You solve the ODE, and whatever remains will be represented like this. So really here I should be more specific and say that X is in up where. And for this, that would mean that we restrict it on the x3 equals 0 plane. So this representation formula does not completely go for this, but you can modify the exponential here to get the full field. But I will send you a reference for this. It does not matter in detail how we do it. The important part is that we can represent this field as a double Fourier integral over something. And that means if we want to have some hope of studying this field using this representation formula, we first need to understand what this something is. And this is a function of two complex variables, so we need to understand what this means. So what are our objectives? What do we want to do? So what can I tell you about F? F is non-singular on R squared for Fi equals 0. So we can assume that this expression makes sense, even if we don't exactly know what that is. But in some sense, becomes singular. Becomes singular. And then the big question is, of course, how to define x 0. How do we define f of x and 0?
Sorry for being fast. Can you ask another question?
On how to estimate f. And this would be the first bullet points that we saw last week for one complex variable. We defined the field in the case of vanishing imaginary part of the wave number. We would like to do the same in this general setting. And we would like to answer the question how to estimate the field as x goes to infinity.
So the second variable, the chi, I guess.
Yes.
So are you thinking of it as a fixed constant, namely the imaginary part of k or k1 or k2? Or are you thinking of it as a variable?
Both. So I first think of it as a constant, and I study my physical problem that I'm erasing relative to that constant.
So you have a whole family of problems.
Absolutely. And then I would like to, and then after I've studied this and I got this, then I treat
as a variable.
that as a variable. Exactly. So even if we don't know how to solve these problems, what we can do is we can write down sort of a functional problem. We can say let f satisfy blah 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 blah, list a bunch of properties that we can formulate using two complex variables, and then we can prove that if we write a formula like this down, we find a solution for our problem. So we know that we can reformulate our physical problem as a problem only in complex variables, and we know how we can estimate this integral. If we have sufficient information about f, which for both of these problems we do have. But first, we need to make sense of what does it mean. Well, first, where is this defined? What are the properties of this? Why does this expression make sense? What does it mean for it to be non-singular? So what does it mean for a function in more than one complex variable to have a singularity? What does it mean to become singular? And then we can try to make sense of both of these points. So this was my motivation for the main thing for today. So several complex. Right. So our goal is to understand all of the machinery that we need to even make sense of a formula like this. Okay. So rotation. So, and we will only be in two complex variables, but everything more or less goes through for n complex variables. So the difficulty is the jump from one to two complex variables, and sort of everything that goes wrong when going from one to two complex variables will also go wrong for higher dimensions. But when you go from two complex variables to 3, 4, or however many you want, nothing big really happens, I would say. That may be wrong, but you can ask Florian about that. So, notation. U is a connected open domain, right? So this is C squared. Do something like this. So, and please check if I do the numbering right. So we say that a function f from U to C is holomorphic. Or what we will use interchangeably is we will also call it just analytic. So when we speak of analyticity, we always mean in complex rivals or in real rivals, but then you can extend rivals. So we will use these notions interchangeably. And I will give you a bit of a weird definition, but it will be the one that's most useful. If is holomorphic, yes, if for all alpha star, so again, under dash denote vectors. In U, the functions. So right, I can fix one alpha, and then I can look at the function alpha 1 is set to f alpha 1 alpha 2 star, or I can look at the function. Right, so I can just fix one or the other variable. So we say that it's holomorphic in U if these functions are holomorphic. Well, let's just say in a sense. Right, these are functions of one complex variable. So we can say that what it means for them to be holomorphic in classical sense. So just your usual one complex variable definition. Okay, I will write a bit more about that. So that means that U bar alpha j, so for j 1 or 2, we have dj alpha bar f is equal to d bar is equal to 0 for d bar alpha j 1/2 d x j plus minus y j where alpha j plus r. Okay, so that's our definition for holomorphicity. And I will not prove this because it's not easy to prove. But as a remark, this definition 4.1 is equivalent to well, let's say statement that f that yeah, I cannot say that f can be approximated by a complex linear function. Right, like this is in real analysis why you can think of differentiability. You can write your function at one point, like you can write something like this. In real analysis, you can write the function like this, that the function at this point plus the differential of this function plus some correction terms which you don't care about. And if it's three differentiable, then this over here is a real linear function. This d of f. Well, and then x. No, sorry, fx. And what this remark means is that our definition is equivalent to stating that we can do this for complex variables, but then df is a complex linear function. And the name of this would be paradox. So if you want to look it up, this is known as the fundamental theorem of power. So it's really important. And essentially what it means that if we choose a clever coordinate system, we can study functions of two complex variables using one complex variable machinery. But it's not a trivial statement at all. But yeah. I will send you also a reference for all of this complex analysis stuff in the WhatsApp group later. So today I will basically follow the Shabbat's book if you know that. Okay. Next. Now, and again, they are connected and open domains such that their intersection is open, connected, and non-empty. Okay. And we say that the fj from uj to c, let fj be another. Then we call f2, let's say the analytical continuation of f1 onto u2. And the other way around, we can say that f1 is the analytical continuation of f2 onto u1. And this statement that it's unique is also not obvious, but if the intersection of two domains is open, then the analytical continuation will always be unique. So I will try to draw a picture. First, that's the first thing, and then I take a picture. So,
Second part, is the definition 4.2 complete?
I think so, yeah.
So you have this.
Oh, no, sorry. It's not complete.
Okay.
So it's the analytic continuation of the one.
It's the analytic continuation
If they agree.
only to
On the intersection. Yeah, sorry. Otherwise, this statement would not have made sense. Yeah, so f2 is the analytic continuation of f1 onto u2 if f2 is equal to f1 on the intersection. And the theorem is that well, the analytic continuation is unique. And we will not prove this because we have a lot of stuff to cover, but well, it's not so straightforward, and I will give you an example as to why it's not necessarily clear that this holds. Because if you would think in the one complex variable setting, you would think, well, if two holomorphic functions agree on a simple accumulation point, they agree everywhere. But this is not true in two complex variables. So I'll give you an example of that in a second. But so the picture is something like this, right? We have our I don't have color. Well, I will look for color in the graph. So I have U1 here, and I have my function f1. I have f2, and I have a function u2, and I have a function f2. They agree on this intersection, and what this theorem and definition says is that this is essentially the same as looking as studying one function f that lives on the union, right? And I analytically continue f1 from here to here. Similarly, I continue f1 from here to here. I will get the same both ways because analytic continuation is unique. So it absolutely makes sense to speak of this function analytic over here. Okay. Yeah, so for some reason I at some point got into the habit of not numbering my remarks. So yeah. I will also not number. So what's important is that in contrast to one complex variable, but it is not sufficient for f1 and f2 to agree on a set with accumulation function. So what would be the counterexample? I have f of alpha, which is alpha 1 times alpha 2, which is absolutely zero on the alpha 1 plane or on the alpha 2 plane, but it does not vanish everywhere in C squared. So this, I absolutely have f equals 0 on the set. And this set has real dimension 2, right? So it's absolutely a set with accumulation point. But f is not 0 everywhere. But I have f not 0 on C squared. So, but when it's open, it works. And of course, these planes are not open in C squared. This is also not the full story, as in you can relax the conditions that you need on the intersection. And in fact, I think this is a whole area of mathematics that studies when you can extend holomorphic functions, when is the holomorphic function.
Varieties, complex varieties, right? It's part of algebraic geometry.
That's probably true. I was thinking about CR geometry, which probably also doesn't do the whole area of CR geometry justice. But my point is that I will not go to the details as to how far you can relax this. We will need open intersections, or we will encounter open intersections, and that is enough. But the proof is still not necessarily trivial, so I will send you references for this later on. I mean, essentially the idea is that if it's open, you can in some sense find a nice real domain in that. So you can extend holomorphic functions into complex variables as power theories. And if the intersection is open, essentially you can reduce it to the one complex variable setting. But for these planes, it doesn't work because the complex planes don't look like the real plane, right? So it's really important how we build the complex numbers from the real numbers. So in some sense, the complex structure is important. And the structure of these complex planes is different from the structure of the real numbers inside the complex numbers. So it's a bit technical, but yeah. So if two holomorphic functions agree on the real numbers in complex variables, they will also agree everywhere. But so what I'm saying is that it not only does the geometry of the set matter, but it really matters the interaction with the complex structure of C squared. But anyway, it will not. Okay. Yeah, so I think I will start talking about singularities a little bit, and then we have our Okay. Yeah, I know that today is a bit dense because we just have to get all the machinery really down. But I will show you some examples in a moment. So definition. So our similarities are called sigma. So let sigma in U and let F from U without sigma even more. So then sigma is called a, well, let's not say we call it a polar, so polar singularity, but full stop. Of F if at every point in sigma the following comes. First, we cannot analytically continue, so there is no analytical continuation of F onto any. So this definition is essentially your one complex variable definition formulated for two complex variables. But the same definition really is the exact same for like any number of complex dimensions. Where was it? So there exists no analytical continuation of F onto any open name UP of P. And two, but what we can do is there we can find a holomorphic function. So there exists a holomorphic function. Let's call it GP, which generally will depend on point P that we consider from UP to C, such that FGP can be analytically continued, can be analytically continued onto UP. Okay, that's our definition of polar singularity.
Such that is the pointwise product F times GP.
Yes, but it needs to hold for every point of P of sigma.
So for such that for all P.
We cannot analytically continue F over, well, not only over P, but right, but so what's the picture? The picture is this is U, this is sigma, this is P, and then this would be UP. So it would say that if I have F, let's maybe make it like this. If I have F over here, then I cannot continue it across P in this neighborhood. So again, so this makes sense because we consider an open neighborhood. So the concept of continuation is applicable. And what we say is that this will not move.
So may I ask a question about it?
Sure.
Because we're talking about an entire set sigma, right? It's like a pole or a polar set.
Yeah.
Right?
Yes.
So you have a singularity at every point.
Yes, right? Exactly.
So that's in one complex variable, you talk about that your sigma is a single point.
Exactly. No, but this will not work, and we will get back to this later.
But so in one variable, you say it's a pole of order k.
Exactly.
Right? In several variables, you can't talk about the order of a polar set.
No, not really, but you can talk. So this is why I just wrote down, we can find a holomorphic function.
Right.
Which
but
we can use
nothing,
to extend.
It can't be z to the something, or I mean, z to this. There is no notion of order associated.
Well, it could be for some examples. In fact, for the example that we look at, I think you could make some order. But the definition is just that sigma is the polar singularity, and at this point, it, you know, it could be a point for that we know. It can't be, but we know. So the definition is just that I have some set in U And we call it the polar set for every point on sigma. I cannot build the continuum F across here. And but I can find a holomorphic function locally at least, such that if I multiply F with that holomorphic function, then it extends through. But this is essentially that we don't why it's a polar, not an essential singularity. So I can, in some sense, I can find a holomorphic function such that this has to remove the singularity. Or that this can be an. Do you all understand this definition of point? But I will show you some examples. Okay. So examples. One, so we can consider this one. Right? It's a rational function, and it has polar similarity at sigma equal all complex numbers such that alpha 1 equals 1 or alpha 2 equals 0 would be by a little bit of use of notation. We write like this. Right? So
one.
oh sorry, it's alpha 1 equal 1 or alpha 2 equals 0. So what we can it's really impossible to visualize these singularities in C squared because C squared has unfortunately 4 dimensions. But we can look at the real alpha plane. Well, we could look at any plane, but for now we can try to visualize the real alpha plane. And then if I would say that this is sigma 1, right? Yeah, and this is, let's call it sigma. Then, well, one singularity is looking like this, and how are you doing it? And the other singularity is just like this, right? So this would be sigma naught, and this would be sigma 1. So, what Loredana mentioned before, we indeed see that the singularities here are not points anymore, right? So there are some two real-dimensional unbounded objects. And in fact, all of the examples that we see will have this feature. And it's not only a feature of our examples, but there is a theorem that tells you that you cannot have compact singularities. Like that, you need to be a bit more careful as to how you state the theorem. But this phenomena of encountering unbounded singularities is that's essentially what happens with the complex variables, and it's one big difference from one complex variable. Right? In one complex variable, you could look at the function like this, which is singular only at alpha 1 equals 0. But as soon as you go to two complex variables, all of these points sort of stretch onto to some unbounded sets. Okay, second example, and then we have the break. Is we could also look at a function like this. 1 minus alpha 1 squared minus alpha 2 squared, which has a pole. And I think it's really straightforward to check that it has a pole. It blows up, it goes to infinity, but like you just multiply it by.
You can find the function.
Yeah, exactly. You just multiply by the denominator, which is a rational function. So that will be holomorphic everywhere in C squared. And so yeah, probably should have said like.
Or even locally, you got a G1 and a G2, which are just
absolutely
-1.
Absolutely.
2.
But yeah, I probably should have said one really important example of holomorphic functions in two complex variables are just polynomials in two complex variables.
So what's the pole?
Oh, yes. So the pole is sigma. Well, right formally, it's just the defining formula for a circle. But this is this does not look like a circle because the circle would be complex. So this is so here sigma is a complexified circle.
Alpha 1 and alpha 2 are complex numbers themselves.
Exactly. Is a complexified circle. So well, I wrote down. It's a bit of a lazy way out, but exercise. Show that sigma is a so what I'm hyperboloid. So sigma, that will be in diffraction. Sigma looks well, maybe I will. Sigma looks something like this. And then it's structured on forever. So this would be sigma would look something like this, but you cannot really imagine how it lies within C squared. But
it has real dimension 3, right?
No,
because
two.
you can solve for if you write alpha 1 and alpha 2 as x1 plus I by 1, x2 plus
exactly, but all of the complex, like the thing that has an I in front of it, must be equal to 0 because
right, because you're saying real part is 0 and imaginary part is 0. The real part is 1 and imaginary part is 0. You're implicitly saying that, right? The complex numbers alpha 1 squared plus alpha 2 squares have real part equal to 1 and imaginary part equal to 0. So that's two equations, it's not one equation.
no, but I don't think that's true.
I mean, on the left-hand side, you have a complex number.
Yeah.
No, of that equation. Alpha 1 squared plus alpha 2 squared is a complex number.
Yes.
And on the right-hand side, you have a purely real number.
Yes.
So for the complex number on the right-hand side, you're saying that the imaginary part
I'd
is
say that
0.
the imaginary times the real part.
The imaginary part of alpha 1 squared plus alpha 2 squared.
Oh,
should be
oh,
0.
yes.
That's
Yes.
two equations.
Oh, sorry.
That's why
Okay.
I mentioned 2.
Okay.
Nice.
Yes.
Nice.
Sorry, I thought you said that the imaginary part of alpha 1 and
The sum.
Yes, yeah.
That's why
Absolutely.
you mentioned
Absolutely.
it's two equations.
Absolutely. Well, now you've already.
No, I mean, we didn't see.
But yeah, essentially, it's what Rodana was saying, that the real part of alpha 1 and the imaginary part of alpha 1 plus
Exactly.
the real part of alpha 2 times the imaginary part of alpha 2 has to be equal to 0. Because
So
we have a
that's
real number.
two equations.
Exactly, it's really two equations that make one. And if you have this, you can write down an equation for the real and imaginary part, and this would be hyperbola. So that's the answer to this exercise. But you can also find some coordinate system which tells you that, which tells you how exactly it's solved. Right, so you can take the real coordinates for the, well, anyway, we have to break now. So
just one last comment on example 1. The question that I was asking about the order of the pole, right?
yeah.
So in that example, one would almost think, trying to say that each of sigma 1 and sigma 2 has, each point is a pole order 1. But if you modify the example and just write instead of that f, you square one of the two factors. So I don't know, 1 over.
Yeah, then you would have 1 is f order 2, the other is 1.
So I'm wondering if one can say, on each connected component of sigma, every point has a constant order. I don't know.
So if you would have, well, anyway, we have to break now for about 5 minutes. Yes, for if you have varieties, singularities, then you can do that as you can switch to the component, which are essentially given by the common effect of like polynomials. So there you can talk about the degree of the polynomials. So that makes sense. But I think I'm not sure this is here, but I don't think. So it's I think it's possible working. In general, I think no is another But analytics, no, looks about the order system are also given as a zero that is some nice polynomial, right? I think this is like bias.
Preparation.
Exactly. So there may be more to it because I know that analytic sets are not algebraic in general, but maybe using the bias preparation theorem, the degree of that polynomial, which we use to define the analytic set, we can, well, I'm not sure if it will work, but maybe there would be a way to make sense, at least of the irreducible components of the order of if the singularity is an analytic set and you split it into irreducible components, which for analytic sets how it works. Maybe you can talk about the order of each irreducible singularity. But at the closing this will break down. But that's
more singularity.
Yeah, but at the closing everything breaks down. So
Exactly. Very good. This is nice. This is really nice. I'm enjoying it a lot.
oh, thanks. Yeah, I feel like I'm going a bit fast, but I have to go fast, otherwise I'm never.
So you're not giving us an example of an F which has a singular set, but the set is not a whole or a full set.
Oh, I will.
Okay, very good, very good. I'm thinking of things like e to the 1 over a 1.
No, I will not. No, but I will. So we will experience.
So can I just interrupt and go back to the stuff we were talking about yesterday?
Oh yeah.
No, but I want to talk about your compliment. So right, before I forget.
Okay, but I've always.
You have.
Yeah.
But can't you move them?
Why?
I was going to make 2 suggestions. Number 1,
I think it's a
in the teaching paragraph.
Yeah.
Mention that your lectures in Bologna are available on YouTube. I just realized this. And number 2, when you talk about your collaboration with Dusty, in parentheses, write something like C applications. So
Oh, but you said that it's about communication.
how you process it? Okay.
So
Too bad, but you should change your CV and add in your teaching experience. You could mention on your CV that this is available on YouTube.
Yeah. But I think for the comments, I think to the course website on my CV. So, but surprisingly, after I submitted, they did not send me a. No, they did, but they did not send me instructions for reference.
That means that they will contact.
Yeah.
Directly.
So I have.
When did you submit your invitation?
Evening. Yes. But anyway, I asked Dusty and I told Dusty that and I did that I didn't tell each about the other, but I heard Dusty also.
Okay.
So well, let's see.
Anche tu partecipi all'organizzazione di questi convegni di questi studenti che ci saranno a Sì, sarai uno speaker.
No, speaker in questo, comunque probabilmente però
Aveva scritto su Spagna. Proprio una bella idea.
sì, certo.
Com'è che si chiama?
La sigaretta capito perché la sigaretta sta
Bellissimo. Senti, quando stiamo lì? Si sta osservando ancora. That's
Oh.
nice. I do it all the time.
Does anyone look this? I get them like around for 50 months now. So.
That's not good advertising.
Oh, it's not. There's no prevention because we are.
That's it, they're fresh today.
No, but then that's more like a loss.
Okay.
Right.
But it's not because they're not old, it's just that I'm trying. And neuron sugars before, you know, the holidays and.
Oh, the times. Well, when did we start the brand?
The questions. GP is
Yeah, exactly. You can also like look locally if you only look at one plane, right? You can only multiply it by alpha 1 minus 1. So I think the detection is
Absolutely.
but yeah, you can just take the
the x-axis.
exactly, just in the real alpha 1 and real alpha.
But that line is really explained.
Exactly. Yeah. It's just if we look at the intersection, so the intersection of these singular planes with the real will look like this.
So we can talk about the complex dimension of the coordinates.
Yes, absolutely. And you can also talk about the complex dimension of a single variable, but it will always be a zero dimensional, right? Plus the points. Which I think, yeah, I think once we
In the first case, it has a convention one complex dimension one.
yes, but that only makes sense on the non-singular. So this is singular so you can talk about the dimension of each complex plane, but exactly because essentially you can singular sets of the singularities, and you can show that away from the singular sets of the singularities. There are some randomness, and then you can talk about dimension, but there are effects that would not make sense. But yeah, so but you can speak about the dimension of each plane. Does that make sense?
Yeah.
And for the circle, you can talk about the complex dimension because the complex of the circle is perfect. Well, yes, you can, and yes, you can. So you can prove that the way singularities are sort of always manuals. So there you can talk about the dimension, but you can say that also the singular ones are itself implementable, but of a different dimension, right? So here the complex dimension is like a single point. So the intersection is whereas away from the singular point, but you're essentially the one point in away from them. Does it make sense? is essentially right. If you would try to look at a cone like this, right? And away from this, you can say that the dimension is 2. And at this point, you can make the dimension is 0. But if you try to assign a dimension to the whole thing in the neighborhood, it doesn't really make sense, does it? Because it's not smooth. You can't find a map that maps it to an open region of any Rn. So the point you can define, as I said, you can prove that the singular sets of algebraic or generally analytic sets are themselves analytic sets. So it absolutely makes sense to talk about the dimension of a singular point like this. And it makes sense to talk about the dimension of something that away from the singular point. So you can talk about the dimension here and at here, but generally it will not be the same dimension. So you can't really find a smooth way. But maybe there is a way that you can talk about this like more algebraic. Right? I'm thinking about it in terms of like smooth manifolds. But maybe if you think about it in terms of varieties, then you can find a way to assign a dimension for all of this. Probably you can. I would be surprised if you can. I don't know. Okay, let's keep going. Okay. So long story short, after we've done it reasonably generally, we will stop being so general now. So what will we say? If sigma is the pre-image of some polynomial, is 0, and so P is a polynomial. Are you guys happy with this notation for polynomial rings? Okay, so it's polynomial ring in the complex numbers in these two variables. Then, well, what we can do is we can write sigma as the union of sigma j, where sigma j is the pre-image of gj of 0. Where gj are irreducible polynomials, right? You can do it for more general class of singularities, but we only need it to be for singularities that are the zero set of some polynomial. And in general, you can not find it as a polynomial, but you can find it locally as a zero set of some polymorphic function. And there are some theorems that tell you that, well, even if it's not really a polynomial, locally it will sort of look like the zero set of a polynomial. So it's not fully general. But you know, everything here, like the philosophy stays the same, even in the general setting. But the general setting is a lot more complicated, and we will only need algebraic singularities. So we will look at polynomials. Yeah, so we will only consider some algebraic singularities. And of course, the examples that we've seen are singularities, right? You can write on the polynomial, right? Well, we've done that. We've written the singularity at the zero set of the corresponding polynomial. So, definition 4.5. We say that sigma j is called irreducible if also, this vector field, so I take the alpha 1 derivative of Gj, and I take the alpha 2 derivative of Gj, and if that is nowhere zero on sigma j, then sigma j is called let me say that it's regular. So,
So, Valentin,
Hmm.
G is a continuous complex value function in the if in the first line up there.
It's a
But-
polynomial.
It's a polynomial.
Yes, it's polynomial in two complex
Let
variables.
me see. So if G is a polynomial, then the singular set is
Well, it's a zero set of some polynomial.
so sigma is the zero set.
So that's our function. We say that if
Okay.
it is a zero set of some polynomial,
Okay.
then sigma splits as the union of the zero sets of G's irreducible
I see.
components.
Yes. Okay.
And
So we're not talking about the singular set, we're talking about a zero set at the moment.
yes, obviously, we think about the singularity, yes. So we will only encounter singularity sigma that are given like this. So we will only consider such algebraic singularities.
So by definition, this particular sigma is an algebraic set.
Yes.
So that's the definition. So an algebraic
Well,
set.
I think I call them algebraic sets. I don't know if that's a general definition.
So an algebraic set is the pre-image of zero via some polynomial, and an algebraic singularity is a singularity that rises.
That is given as, and that is an algebraic set.
Right, because it's not a singular set for G.
No, it's not a singular set for G. No, it's a zero set.
Okay.
And if in addition, the gradient, the complex gradient of Gj is nowhere zero on sigma j, then it is called regular. So one counterexample would be, well, actually, I think all irreducible. If we write it down like this, then all irreducibles should be regular. But don't quote me on that. Anyway, if we think of it in a more general setting, then we absolutely need this additional condition. So
Is that a matrix or is that the determinant of some matrix?
it's a gradient. The gradient,
It's the gradient.
like the complex gradient.
So you're taking the complex gradient of Gj
Yes.
on sigma j, and you're asking for the complex gradient to be non-homogeneous.
Yes.
Okay.
And if that is the case, then we call it regular. And we will only consider sigmas that satisfy all of them. So,
Sorry for being a pest.
no worries.
So does that mean, Valentin, that by considering only such singular sets, that means that the homomorphic functions that you work with are of the form 1 over G of alpha 1 and alpha 2?
I don't think so, but I don't know.
Okay.
What?
If I take the function 1 over G, given G,
Yes.
if I polynomial, if I look at the function 1 over G, that's a function which has a pole given by that sigma over there, right?
Yes. Absolutely.
But those are not the only functions that you work with.
Yes.
One of the type 1 over polynomial.
Yes, that is true.
Okay.
Because you could have multiple singularities, and you could also have branch sets. So if you turn around, you could also have branch sets, which we will see.
Branch sets. Okay.
So then you could turn around one, and then on the other sheet you would discover other singularities, and then on the other sheet you would discover even other singularities. So it's not so locally you can describe it like this, but that doesn't mean that you can necessarily write it globally, right?
Okay.
It's essentially like a Laurent series, even if you can locally represent a holomorphic function.
That's not a global.
It's not necessarily a global thing exactly. So yeah.
So locally, it's true that it's always polynomial, 1 over polynomial. Because
The singularities.
yeah.
Yeah.
Okay.
that the function is locally
Yeah, because
given by one.
I don't know if it's locally, but well, wait, that's two different things, right? If the singularity is locally is given by this, then it means that locally you can multiply a function by a polynomial such that then you can extend it. But that does not mean that the function itself was a polynomial to begin with.
So in other words, if we have a function p, a function f, that is singular, that has poles along that set for some polynomial g. So that means that p times g, f times g becomes holomorphic.
yes,
Look, I am.
But f has not be itself polynomial g.
Let's look at this. It has a pole.
Exactly.
This is an identified policy.
So that would be an f.
You can remove it by multiplying by 2, which itself is a polynomial, but the function itself is not a polynomial.
but if I take 1 over e to the g minus 1,
What's
So that's right. That's right. 1 over e.
to the g minus 1, g is a polynomial
Yes.
for 1 and for 2, and then I go under, I have
In the denominator, you have that exponential minus 1.
yes.
Minus 1.
Locally, this can be expressed by the polynomials, the denominator, but
When you look, you can represent it as power series.
yes,
Right.
But that's only polynomial if it's silent. Otherwise, it's like it's so much. Yeah, but like locally, you can always use power series. So if you say that after you extend it, you can write it as a power series, that's always true because then it's power.
So what Valentin was saying is that.
But it doesn't necessarily define it in terms.
But it's not a polynomial, right?
yeah,
Yeah, but that I agree. Yeah,
yeah,
no, absolutely, yes. Because so
Like
that works in several complex variables. You can always expand a holomorphic function locally as a power series. That works in several complex variables, just as a complex variable. But the expansion is a bit more complex.
But the point is that you want to be able to locally multiply times a polynomial, which is finitely many terms, and
Yes,
get a holomorphic function.
exactly. But the function that has the singularity is not even locally.
Itself doesn't have to be polynomial.
Exactly. So definition, what we need. The definition is going to be it's going to be a bit of a mouthful for bearing with me. So what we consider now is we consider a path. So let that be smooth. And let U1, UM be a finite covering of gamma of 0, 1 such that gamma 0 is in U1, gamma 1 is in U1. And QI UJ with QJ plus 1. It's not empty. And oh, okay. Okay. So you can always find a covering like this because this is compact. So that will always work. So it's open and connected, and so we say that F1 going from U1 to Z admits an elliptical continuation. So this is essentially the 1D definition, just formulated into parameters. Along
Gamma.
gamma, and maybe right. Along gamma. If for all j, there exists an fj plus 1 going from uj plus 1 to c, that is the analytic continuation of fj.
So
Going from u to j.
So this is terminology. So we're saying that F1 admits an analytical continuation.
Yes.
If along gamma, if for every j there is an fj that is the analytical continuation of fj.
Yes.
So you can have more than one analytical continuation along gamma.
No,
You're saying
no.
okay.
It will be unique along gamma, but it is so. Yeah.
So it has to be proved.
No, this is really straightforward because you can look at the intersections of the open sets, and you know locally it will always be unique. But the covering is chosen to be around the path. Well, you could. I'm not saying that it's the maximum domain, but every other covering, open covering that I choose, has to be around the path.
The fact that you're writing n instead of the analytical continuation has to do with the fact that you can change the covering.
Yes.
So if you fix the covering, the analytical continuation along gamma is unique.
Yes. And I can always speak about the value that f takes at gamma 1 subject to this analytical continuation, because what you could have is you could have one point and you could have one path. But you could also have another path, and then maybe two different values. But along this path, I will be able to say what this is, given that I've started from here. So this will make sense. So I can talk about this for both of these paths. So again, what is the picture? Well, I didn't really look for color in the break, so sorry for that. So this is gamma 1, U2, and let's say U1 here. I have gamma of 0, and this is gamma, and then I have F3, F2, F1. And this family is well, it's linked to the covering that I've chosen, right? But assuming I fix the covering, then so this I started with U1, F1, and with a path. And what the definition says, if I can then find U2, U3, F2, and F3 like this, then I can make sense of a function f that lives in here. And for this function, I can then say what value does it take at gamma of 0 and at gamma of 1. And the value that it takes at gamma of 0 and gamma of 1 will be independent of the covering, because every covering has to be an open neighborhood of gamma. So if I take if I then want to have uniqueness, I can look at the intersections, and that will be some of the different type of covering, which itself will be open. So then I can use uniqueness. So along the path, it will be unique. Okay. This is super important. We understand that. Okay. So we are. Yeah, I think we can actually get over
that FJs must be homomorphic.
Yes, absolutely. Sorry.
F1, 2.
Yes, my FJs are always homomorphic.
Yes, this is analytical
We say that F1
So we're assuming that F is an
for all that there exists, yes. There exists Fj plus 1. Homomorphic, that is in a continuation.
And F1 is homomorphic.
Okay, exactly. So F1, yes, so that F1, which is holomorphic, and then we can iterate, right? If F1 is holomorphic, then I say that I can find F2 holomorphic that extends it, then I can find F3 that extends it, and I repeat that. And after finitely many iterations, I'm done. And it will always be possible to be done after finitely many iterations because the path is compact. Okay. So let C part A. Irreducible. As a reminder, now by irreducible, I always mean that it's also regular. So let this be irreducible. So what we do now is we choose a very nice coordinates. And not this similarity.
So fast, we don't
so near P. Wait, sorry. No, that was at P is sigma day, and let UP be open. Okay. So near P, that by near P I mean sufficiently small such that everything that I'm about to write makes sense. Near P, let Z of alpha equal to some kind of, I will tell you what this in a moment. Gj alpha and T of alpha is one beta dash dash. It's not the derivative of anything itself. The alpha 2 Gj evaluated at the point P alpha 1 minus P1. So yeah, I'm doing this with one effect. I'm sorry. So P is P1, P2. And I said that if I have something like this, it's always a vector X step when it's P. Well, it's still has components. So it is this. Now it's going to be alpha 1 G J P of alpha times alpha 2 minus P2, and this is so beta and beta dash are real constants, and they are not zero.
The betas are constants.
Real non-zero constants. Yes. Just think of them as being one. That will be.
And there's a minus there, right? It's minus the
minus the alpha 2 derivative plus the alpha 1 derivative.
Okay.
So it's minus the alpha 2 derivative of Gj evaluated at P times alpha 1 minus P1.
And those are the complex derivatives, right? In alpha.
Yes. Yes.
So Z of alpha and T of alpha. So these are so the Z of alpha is just a multiple of a polynomial.
Exactly.
And T of alpha is a linear function, right? It's a polynomial of degree 1.
Yes.
Right?
Well, depends if G is the polynomial. Well, no, absolutely. You're right. You're right. Yeah, it always. So if I evaluate.
The variables are.
Yeah. So this is a constant.
Exactly. So this is polynomial.
Absolutely. So, and this, well, this is right? Because this is irreducible, this will always be non-zero. So then you can check for UP sufficiently small, and leap small. This is Python. So it is a complex change of variables, and generally that will only work locally. If you want to prove that, you compute the determinant of this, look where the determinant is non-zero, and use implicit functions.
So this is biholomorphic from UP.
Yes. It's for UP.
Okay.
This is biholomorphic change.
Okay.
Variables.
So the idea is to map alpha 1 and alpha 2 into Z and T.
Yes. Yes. On variables on UP. And this is why we do all of this. If I look at the intersection of now sigma j with UP, it will be the set of all that P in UP such that Z is equal to zero.
You're flattening.
Exactly. So
this is for every beta prime and beta double prime. The binomorphic change of coordinates is true for any choice of beta prime and beta double prime.
If they're non-zero.
For non-zero real value.
It may not necessarily be orientation preserving, right? So I could change them to be one or the other could be minus. That would change the orientation.
Okay.
But if they are non-zero, then even if they are complex, then it would still be a biholomorphism. But if they are real, it will also be a real change of coordinates. So that's the important part. So it's a biholomorphic change of variables. And assuming this intersection is not empty, which it could be, but if it's empty, the statement is still true. It is a real So if this set is empty, then it is still a real change of variables. It's just the empty set. So that will always work. But if it's not, but also if it's non-empty, it's a real change of variables. Good. So what is the picture? If we look at we could look at the plane, but then it's really not so interesting. But we can look at the complexity of circle. So I really need to cross.
There was a little bit of orange today.
Yes. I found my green chalk. Look.
There you go.
Well hidden. I also pictured. Anyway, so we would have T sort of like this. So this would be T. And then sort of going out, we have Z, which is also has 2 degrees of freedom, but we can't really draw it. So this is the best that I can find. And here this, and here we would have P, right? And you can sort of see that this is really only a local property, because if it was globally possible, that would tell you that the cylinder is locally looking, or the circle is locally looking like R2, which is not the case. So it really is a local property. Right, and then we have, so this is the Z plane, where you have P1. So the coordinate system is centered at P, right? Because in this coordinate system, P is just 0, 0. So we have the coordinate system centered at P, and it will extend a little bit, but not necessarily everywhere. But for the planes that I've shown you, it would extend to the whole plane. And if you are interested in trying to find something like this, not for the irreducible components, like try it for the example that I've shown you with the planes, where both planes are intersecting, And you will find that it will not work because at the intersection point, the defining function would have vanishing gradient. But it's not a bad exercise to try and, you know, to try something like this for non-irreducible singular sets. Okay, and this is T. And here I have P2, and well, sort of here. So here I have only, the sigma is only P1, right? But here it really is everything. So what Loredana said, I flattened out my singularity. In this coordinate system, you can see T lies completely on the singularity. So the entire T plane will be singular. Well, entire T plane is wrong, right? Because you look at it locally, so you would have an open set. But morally speaking, the entire T plane will be singular. And here it's only going to be a single point. Why is that super nice? Because this single point is exactly what we are used to from one complex fiber. So we can use this coordinate system to study singularities using one complex variable machinery. And you can find such a coordinate system for a more general class, like for every singularity, I think. So don't quote me on that, but I think that for every singularity you can find, well, for every regular singularity you can find that, not in general, but well, more precisely for any analytic set, which does not need to be an algebraic set, but anyway. We will always be able to find this because we are looking at algebraic sets. Okay, where was I? Yes, so, oh my God, I have, yeah, I'm sorry, I have 1 minute left, but so maybe we'll go 5 minutes overboard. Is it okay? Because I'm almost done. And it's really important that I define what it means to be a branch set. And it is also, I think, important that we do all of this in one go, because if I try to tell you about it next week, you will have probably forgotten half of today, which and same with me. So I will define what it means to be a branch set, and then we're done. So 4.7. Let you okay, use always open. So let F okay be another. Let sigma j be irreducible. Let the definition be the mouthful. That P in sigma j and use our Z P coordinates as well. Disclaimer, I will write the definition in coordinates, but you can show that it's independent of coordinates, but it's not trivial. So you would need degree of a map to show that what I'm about to write down is independent of the choice of coordinate system. But once you have the degree of a map, once you understand that, then it is reasonably straightforward. But the concept of a degree of a map is not so straightforward to understand. Okay, as above. So we call sigma j a branch if and only if the following is. One, there exists an analytical continuation of F along the path gamma of tau, which is in the ZT coordinate system, given like this. So what that means is that gamma looks like this, right? So which yeah, here would mean that it sort of moves around like this. So you cannot imagine how it moves around the set in general. But if you choose this coordinate system, then you can speak about it. And topologically, if you want to do it without coordinate system, you would say that I think it's called linking number, that the linking number of this map around this set is no, sorry, you would have to be more precise, but I don't worry about it. So you can say about how many times something binds around another object using the notion of linking number. And then you could say, and then you could define that, right? You could say that if something is linking number blah blah blah, then you can analytically continue blah blah blah, and then you can choose about coordinate system. But anyway, the definition is not finished. If there exists an analytic continuation of f along
So a circle in one, just a circle.
yeah. And two, this is the important part. So it's a closed circle, right? It returns back to itself. And f of gamma of 1 is not equal to f of gamma n 0. So, and if there exists an n smaller than infinity, such that f of gamma, if I now wind it around n times, then if there exists an gamma, n smaller than infinity, such that this is equal to that, right? After I wind around it finitely many times and I return back to the original value, then we call n the order of sigma play.
So there is some notion of order.
NP.
And n is an integer, right?
N is an integer, yes, yes, yes. N is an integer.
This is the definition.
This is the definition.
Okay, just give us 1 second to start digesting it. F is analytical mu.
Yeah.
No,
Ah,
wait.
sorry. Thank you. No, I did not mean to erase that. Oh, sorry.
You.
Oh, it's a very fascinating number.
F is analytical mu. Just
Oh.
1 second.
Sorry.
You're so fast. Okay.
Well, it's important.
Sigma is irreducible. P is a point in sigma.
Yeah.
And so now we have this local
Yes.
coordinate change. And we say that sigma j is a branch if and only if. So are we saying that how is this curve gamma, this circle,
Yeah.
related to the set sigma? It seems to be part of sigma, right? In this local coordinates. Is gamma contained in sigma or after the change of variables?
No, that's exactly the point. Gamma winds around sigma because in this coordinate system locally, sigma is given by this. It's centered at the origin, and this only.
It's not in sigma.
It's not in sigma. It's in the z plane.
It's in the subplane and it surrounds the point P.
Exactly.
That's
So it is not in sigma. That's the important part.
okay.
So this is what I try to sort of, in a bad way, say.
It's a bridge point. So
Yes.
X is defined along gamma
Yes.
because it's analytic in mu.
Yes.
Right, but f of gamma of 1 is different from f of gamma of 0.
Yes.
But just a second, gamma is contained in u.
Yes. 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 Yeah.
And f is analytic in u.
No,
No.
sorry. No, gamma is the UP, but UP is not.
So say that again, I'm sorry.
So the picture would be that I
So
have,
f is analytic in u,
yes,
but
but here I would have
up.
UP.
So u is contained in up.
Yes. Yes.
And gamma of t
Yes.
is contained in up.
Yes,
So F is not analytic in P, it's only analytic in U.
exactly. And then we can analytically continue it, but the value that we get after analytical continuation may be different from the value that we start.
And so just a second, do you have gamma to the n of 1, but you don't have gamma to the n of 0? Gamma of 0 in the
Yes.
second equation.
Yes,
So gamma to the n of 1, it means that you are
I find it wrong n times.
n times until you find an n such that for the curve gamma to the n, the value of f at 1 on the curve is equal to the value of gamma of f at gamma of 0, the original curve.
Yeah.
Okay, I think we should stop here.
Yes, this is also where I
I
want.
definitely need time to digest it.
So we stop now. I will write down, if you want to see some examples, well, maybe I can just send it to you on the WhatsApp. Well, for example, if you would look at, you can pick up. So if you would look at this, then the branch would be this, and the order would be 1, right? But there is a more interesting example, but maybe I will show that next week.
And maybe when we resume next week, can you start by putting this definition again?
Yes. Yes. Okay, wait, so I will quickly stop the Zoom recording, otherwise everyone will be horrified.
But, gamma 1.